long context models are crushed by their own memory. A 32,000 token context for an 8 billion parameter quen holds roughly 19 gigabytes of key value cache, and every decoding step drags through over a gigabyte of it. Dynamic sparse attention promises to cut that cost by touching only the few tokens that matter. But in real serving systems, the promise leaks away. A 2026 paper called Spin argues the leak is not in the attention math, it is in the runtime. Two failures erase the sparsity win. First, every new sparse algorithm ships its own bespoke key value manager, so nothing is shared, optimized, or reusable. Second, sparse attention grabs small scattered token subsets that change every step, so the graphics card pulls them across the bus in irregular bursts that waste bandwidth and stall the decode. The attention is sparse, but the data movement is bloated and unpredictable. Theoretical sparsity never becomes real throughput. Spin, built on VLLM, abstracts every sparse algorithm into one 5-operation pipeline. 3 operations are algorithm-specific. Index organizes tokens into partitions. Select finds the critical partitions for the current query. Attention computes over them. 2 operations are shared. Offload materializes partitions across the GPU and CPU tiers. Retrieve pulls missing ones back. The unifying unit is the partition, a token group that maps algorithm sparsity onto hardware-efficient pages. 3 design decisions follow: partition, abstraction, locality-aware, bucketed LRU management, and OS-style hierarchical metadata. The headline, across 3 models and 2 long context benchmarks on A100 and B200 GPUs. Spin sustains 1.66 to 5.66 times higher end-to-end throughput than VLLM and 7 to 9 times lower time to first token. It does this by slashing per-request GPU memory demand, so the server packs larger batches. Spin holds 2.5 to 3.3 times bigger average batches while VLLM plateaus and thrashes. The cleanest result isolates the runtime from the algorithms. Run the same sparse method under Spin and under its original implementation. Shadow KV decode latency drops 21% at batch 1, 35 at peak. Retro infer drops 22 and 8.4. Seer attention drops 47 and 58. The envelope is 8.4 to 58% lower decode latency, up to 2.39 times throughput from runtime engineering alone. Here is the picture. A flat per head page table, pre-allocated for long context, blows up to 100 gigabytes of GPU metadata for a 70 billion model. Spin replaces it with a 2-level OS-style index that scales with the physical working set, not the worst-case address space. The hierarchical metadata cuts HBM consumption 49 to 78 times. Same attention, a fraction of the indexing overhead. The locality lever closes the rest of the gap. Autoregressive decode reuses critical tokens across consecutive steps. Spin's bucketed LRU keeps a per-request buffer of mandatory pages plus reuse pages. Adding the buffering layer lifts decode throughput 49%. Hit ratio saturates once the buffer is 4 times the mandatory set, so the scheduler stops trading concurrency for cache beyond that. 2 honest caveats. First, per-token decode latency is higher than dense VLLM because retrieval sits on the critical path. The win only amortizes at high concurrency, so single-user chat is not Spin's regime. Second, on B200 at small batches, Spin's decode throughput falls below VLLM because newer GPUs have enough bandwidth to absorb dense attention. Spin retakes the lead as batches grow. This is a high-throughput serving system, not a low-latency one. Spin reframes sparse attention from a math idea into a serving runtime. The payoff, up to 5.66 times throughput, 7 to 9 times lower time to first token, 49 to 78 times less metadata memory, and 8 to 58% lower decode latency than the 1.5 operation pipeline and a partition abstraction let 3 different algorithms share the same optimized data movement. Original implementations. The paper is Spin. Subscribe for the next breakdown.